In previous videos, we used the Aufbau principle and Hund's rule to construct orbital diagrams and electron configurations for the first 10 elements of the periodic table. As the atomic number increases, the number of electrons in the electron cloud is greater, and we need new tools to assist us to write electron configurations for these big atoms. This diagram shows us the orbital diagrams and electron configurations for the first 10 elements of the periodic table. As a reminder, we can see that when the atomic number of an atom or element increases, the number of electrons in the electron cloud also increases, and we have seen that the structure and distribution of electrons within electron clouds builds up in a special way in accordance with the Aufbau principle and Hund's rule. But as we progress through the elements and work our way up to larger and larger numbers of electrons, it starts to get confusing as to which orbitals and subshells need to be filled first in an orbital diagram such as this. This is particularly true by the time we get past element number 18, argon, with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. And we can see the order of filling electrons for the argon atom, starting with the 2 electrons in the 1s subshell, followed by 2 electrons in the 2s subshell, then 6 electrons in the 2p subshell, which fills the entire n equals 2 shell. Then we progress to the 3s subshell, where we place a further 2 electrons, and finally the 3p subshell, where we place the final 6 electrons. Now, to progress to element number 19, potassium, we might expect to continue to fill the 3d subshell, which is the next subshell in the n equals 3 shell. However, as we've noted before, the 4s subshell actually lies lower in energy than the 3d subshell, and so, according to the Aufbau principle, needs to be filled first. And so to get the orbital diagram of potassium, we need to add the 19th electron to the 4s subshell at the top left of the diagram. This gives the electron configuration as the same as argon with the additional 4s electron, that being 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. For the next element, calcium, number 20, the 20th electron is also added to the 4s subshell, paired with the first, to give an electron configuration for calcium as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And given that the 4s subshell is now full, the 21st electron for the element scandium is added to the next highest energy subshell, being the 3d subshell, to give an electron configuration for scandium, element number 21, as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So as you can see, it can get quite confusing as to which subshells to fill first when we start filling orbitals and subshells at higher energy levels, where the energy levels of orbitals and subshells get closer and closer together. To help with this confusion, we can use a simple mnemonic diagram called the Aufbau diagram, and we use it to remember the order of filling of subshells. To generate the Aufbau diagram, we start by writing out the subshell designations for each subshell within a shell, starting with the n equals 1 shell. The only subshell in the n equals 1 shell is the 1s subshell. When we go to the n equals 2 shell, we note that there are 2 subshells, 2s and 2p. There are 3 subshells in the n equals 3 shell, namely 3s, 3p, and 3d. We continue writing for the other levels, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, although in practice we will never have to get to the 5g level. But we will need to go to 6s, 6p, and 6d, and 7s is generally as far as we need to go. So this is the Aufbau diagram, which we can use to determine the order of subshell filling. The order of subshell filling is determined by drawing 45-degree lines back through each of these subshell labels. So, as we know, the 1s subshell is filled first, followed by 2s, followed by 2p, and then 3s. The filling of the 3p subshell is actually followed by filling the 4s subshell, as we've just discussed, before we start to fill the 3d subshell. The 4p and 5s subshells fill up before the 4D subshell, and so on 5P and 6S, followed by 4F, 5D, 6P, 7S, and then 5F, 6D. And that's about as high as we need to go, since by this stage we will have gone past uranium, element number 92, it being the last of the naturally occurring elements. The other thing we need to remember is the number of electrons that each subshell can accommodate. All S subshells have only one orbital and so can only accommodate 2 electrons. All P subshells have 3 orbitals and so can accommodate 6 electrons. All D subshells have 5 orbitals and so can accommodate 10 electrons. And all F subshells have 7 orbitals and so can accommodate 14 electrons. Let's use the Aufbau diagram to generate the ground state electron configuration for bismuth, which has an atomic number of 83 and therefore contains 83 electrons in its electron cloud. Bismuth is located in period 6 and group 15 of the periodic table. And basically, once you're able to generate the electron configuration for bismuth using this approach, you'll be able to generate the electron configuration for any other element. We'll start at the bottom of the Aufbau diagram and start by filling the 1s subshell, which we know holds 2 electrons. So we start with 1s2. So that is 2 electrons we've used up in the 1s subshell, and the cumulative count so far is 2 electrons. Next we go to the 2s subshell, which we know also contains 2 electrons. So we write 2s2, representing 2 more electrons, so the cumulative count is 4 electrons. So we've used 4 electrons up so far, and remember we need to stop at 83 electrons for bismuth. Next we fill up the 2p and 3s subshells, which we know have 6 and 2 electrons respectively, so we write 2p6, 3s2, using up 8 more electrons for a cumulative count of 12. Next we fill up 3p and 4s subshells, which again have 6 and 2 electrons respectively, so we write 3p6, 4s2, using up 8 more electrons for a total count of 20 so far. Next we fill up 3d, 4p and 5s subshells, which we know have 10, 6 and 2 electrons respectively, so we write 3d10, 4p6, 5s2, using up 18 more electrons for a total count of 38 so far. Next we fill up the 4d, 5p and 6s subshells, which again have 10, 6 and 2 electrons respectively. So we write 4d10, 5p6, 6s2, using up 18 more electrons for a cumulative count of 56. So we're starting to get close to our number of 83 electrons for the bismuth atom. Next we fill up the 4f, 5d, 6p and 7s subshells, but we know we only have 27 more electrons left, which will fill up all of the 4f subshell, using up 14 electrons, and we will fill up all of the 5d subshell, using up 10 electrons, leaving us with only 3 electrons to place in the 6p subshell, which will only fill half of that subshell. So now we write 4f14, 5d10, and only 6p3, using up the remaining 27 electrons for a total of 83 electrons for bismuth. To get the full electron configuration for bismuth, we simply string all of these individual configurations together to get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p3. Now, an electron configuration is supposed to be a shorthand notation, and this configuration here is hardly that. In the next video, we will be introduced to a very simple method for writing condensed versions of these rather long electron configurations.